Okay, so for today's do now, it's going through bond polarity, so going back to the beginning of the week with bond polarity, and then looking at Lewis structures and starting to look at formal charges. So what we're going to do is we'll just go through all of this together, especially with the bond polarity, and then question 6 is going to kind of be our transition into looking at formal charge and resonance, which was the video last night. So for numbers 1 through 4, it says determine if the bond is ionic, polar covalent, or non-polar covalent. And then I said try to do them without using electronegativity differences. So without using electronegativity differences just means we're going to look at the periodic table. So before we go into looking at each of these 4 and classifying, I want to go through and just do a quick review of the 3 types of bonds. So for an ionic bond, remember that ionic is completely different than covalent because the electrons are transferred. So in an ionic bond, electrons are completely transferred from the metal to the nonmetal. So we have a metal and nonmetal in an ionic bond. So ionic bonds are just an attraction between a cation and an anion. When we get into covalent, so whether it's nonpolar or polar, covalent is all nonmetals. In a polar covalent, the electrons are shared unequally. So they're not equally shared. In a polar covalent bond, it's like a tug of war. One side of the bond is pulling on the electrons more than the other. That's when we notice an electronegativity difference between the 2 atoms. Nonpolar covalent, the electrons are shared equally. So in a nonpolar covalent bond, essentially we have an electronegativity difference of 0, or something very close to 0. So nonpolar, it's even sharing. There's no tug of war. They're sharing them equally between the 2 atoms. So for numbers 1 through 4, we'll start by identifying ionic. So in an ionic bond, we should have a metal and a nonmetal. So looking at numbers 1 through 4, there is one of them that is ionic. Which one is ionic? 1, 2, 3, or 4? Number 4. Number 4 is ionic because sodium is a metal, iodine is a nonmetal. So without even looking at electronegativity differences, we can tell that that's ionic. Then when we look at the rest of them, these are all covalent. So now we need to look at, is it polar or is it nonpolar? I had said a couple days ago that CH bonds are always nonpolar. So if you didn't remember that a CH bond is always nonpolar, make yourself a little note. A CH bond is always nonpolar. So it's equal sharing of electrons between the carbon and the hydrogen, because carbon is an atom that's not very electronegative. So when we look at 2 and 3, some other things to keep in mind. Fluorine, oxygen, and chlorine. So fluorine, oxygen, and chlorine are the 3 most electronegative atoms. So typically any bond that has F, O, or Cl will be polar, with the exception of the atom bonded to itself. So an FF bond is nonpolar, an OO bond is nonpolar, a CL-Cl bond is nonpolar because it's an electronegativity difference of 0. So going off of the idea that anything bonded to F, O, or Cl is polar, that tells us that 2 and 3 are both polar covalent. HF is an extremely polar bond. Fluorine is the most electronegative atom on the periodic table. Anything bonded to fluorine will make a polar bond. And then typically carbon bonded to any halogen will also create a polar bond because carbon is not very electronegative, the halogens are. So that's looking at 1 through 4. Number 5 says draw the Lewis structure for carbon dioxide. So if we're looking at drawing the Lewis structure for carbon dioxide, the first thing we need is the formula. It's the formula for carbon dioxide, CO2. So as we go through and we draw the Lewis structure, we just go through the steps. The very first thing that we do is we count up valence electrons. So if we look at the periodic table, carbon has 1, 2, we skip the middle, 3, 4 valence electrons. Each oxygen has 6. So 12 plus 4 is 16. There are 16 valence electrons that we have to place in the Lewis structure. And we make a reasonable structure. If carbon is present, it is always the central atom. Carbon is usually the least electronegative atom that is in the molecule. When you draw the structure, you always have to ask yourself, is there the potential for multiple bonding? Do we have part of cons bonding with part of cons? And in this case, yes, we do. C potentially bonding to an O, they're both part of cons, which means we have to do the 6n plus 2. 6n plus 2 rule helps us to determine what kind of multiple bond we need, if any. N is the number of atoms in the molecule, not hydrogen. So 1, 2, 3. There are 3 atoms in this molecule, 2 O's and 1 C. So 6 times 3 is 18, plus 2 is 20. We compare 6n plus 2 to the valence electrons. When you look at 6n plus 2 compared to the valence, you have one of 3 things that happen. They're equal, in which case it's all single bonds. 6n plus 2 is 2 greater than the valence electrons, in which case you need 1 double bond. Or it's 4 greater, in which case you need either 2 double bonds or 1 triple bond. So because this is a difference of 4, we need either 2 double or 1 triple bond. Now when we look at this and we say 2 double or 1 triple, well, you could technically put both. So we're going to go ahead and we're going to show both of the possible carbon dioxide structures. If we had 2 double bonds, we'd have a double bond on each side of the carbon. If we had 1 triple bond, we'd have 1 triple between a C and an O and a single between the other one. Now let's make sure the octets are filled with each. Carbon is good with 8 on both. Up here, oxygen only has 4, 5, 6, 7, 8. Oxygen has 4, 5, 6, 7, 8. Down here, oxygen only has 2. Here, oxygen has 6. So for carbon dioxide, we could have one of 2 structures. Now, one of these is better than the other one, and we're going to look at how to tell on the next slide. But for now, we could have either one of these as a structure. Again, we'll go through how to tell which one is better and why we only see one of them when we draw CO2. For number 6, calculate the formal charges on each atom of each of the following Lewis structures for thiocyanate. And then based on formal charges, which Lewis structure is dominant. So down here we have 3 different structures. We have A, B, and C. All 3 of the structures are SCN-, but the bonding is different in each one. Formal charge is a way for us to determine which structure is the best. So what I'm going to do is I'm going to rewrite them up here so that way everybody can see them. So the first one, structure A, looks like this. So we'll do A first. The first thing it wants us to do is calculate formal charge. Now if you want to memorize the formal charge equation, you can. I don't even remember the formal charge equation because I just use circles to calculate formal charge. So when I want to calculate formal charge, I'm going to draw a circle around each atom in the molecule. I'm going to cut the bond in half. I'm going to draw a circle, and I'm going to cut the bonds in half. So I have a circle around each atom. To calculate the formal charge on each atom, we will do the valence electrons minus the number of electrons in the circle. So valence electrons minus number of electrons in the circle. So if you look at your periodic table, how many valence electrons does sulfur have? 6. So sulfur has 6 valence electrons. I'm going to subtract the number of electrons that are in this circle. So I have 1, 2, 3, 4, 5, 6. The bond gets cut in half. So 1 electron goes to sulfur, 1 goes to carbon. So there's 1, 2, 3, 4, 5, 6, 7 electrons in the circle. 6 minus 7 is negative 1. Carbon has 4 valence electrons. Count up the number of electrons in the circle. 1, 2, 3, 4. 4 minus 4 is 0. And then for nitrogen, nitrogen has 5 valence electrons. And there's 1, 2, 3, 4, 5 electrons in the circle. So for formula A, sulfur carries a negative 1 formal charge. Carbon and nitrogen both carry formal charges of 0. So to calculate, all we have to do is valence electrons minus the number of electrons in the circle. So if we look at B, now we're going to look at the bonds being located in a different place. It's going to look like this. And the brackets are because it's an ion. So let's do the same thing. Circles around each atom and cut the bonds in half. You guys already told me sulfur has 6. You said carbon has 4, nitrogen has 5 valence. Then you subtract the number of electrons in the circle. So sulfur, 1, 2, 3, 4, 5, 6. 0. Carbon, 1, 2, 3, 4. Formal charge of 0. Nitrogen, 1, 2, 3, 4, 5, 6. Formal charge of negative 1. So for B, sulfur and carbon have formal charges of 0. Nitrogen has formal charge of negative 1. So A and B are similar. It's just the negative is on a different atom. And then finally, we'll look at how the bonding in C affects formal charges. So we have this Lewis structure for C. So now again, circles around each atom and cut the bonds in half. Valence electrons for all of them don't change. What changes is the number of electrons in the circle. So sulfur, 1, 2, 3, 4, 5. So that's plus 1. Carbon, 1, 2, 3, 4. Still 0. And nitrogen, 1, 2, 3, 4, 5, 6, 7. Negative 2. So for C, we have plus 1, 0, negative 2 for formal charge. The whole point of formal charge is to determine which Lewis structure is the best, which is the one that we're going to see most often. And that is the one that has the most atoms with a 0 formal charge. And if there has to be a formal charge, it puts the negative on the most electronegative atom. So in terms of most electronegative, we would see F, O, Cl, and N are going to be the 4 most electronegative atoms. So I'm going to eliminate C right away, because C has 2 atoms that have a formal charge. Only one has a 0. Where in B, 2 of the atoms have zeros. So between A and B, what we're looking at is where the negative is placed. We always want to place the negative on the most electronegative atom in the molecule. So between S and N is the more electronegative atom. So B is the best structure. Again, because it has two atoms with a formal charge of 0, and if there has to be a formal charge, it puts the negative on the more electronegative atom. N is more electronegative than S because it's smaller. So to start, I want to go over just a few questions that people had on last night's video. So the first one was looking at exceptions to the octet rule. So beryllium and boron are exceptions because they are such small atoms. Beryllium only needs 2 electrons, so it also satisfies the duet rule like hydrogen. And boron actually only needs 6 electrons in the valence shell to have a satisfied octet. Right, but it only needs 6 electrons. Now, one of the questions in the video was, could boron potentially have 8 electrons if it was bonded to other atoms? And the answer is yes. We could potentially see boron having 8 electrons, depending on what it's bonded with. But if you have something like BH3, in which boron and hydrogen are both small atoms, boron only needs 6 electrons to have the octet rule satisfied. So if you notice that you're adding up valence electrons, and for BH3 you only need 6 electrons, it's okay if boron only has 6 electrons around it. We'll look at formal charge and resonance today, but as we look at resonance, we are going to go back and review bond order. So from video 1.7, bond order is the number of chemical bonds between 2 atoms. So when we talked about bond order at the beginning of the week, we said a single bond has a bond order of 1, double bond is a bond order of 2, triple bond is a bond order of 3. But when we look at resonance, we're going to look at how bond order changes because of that hybrid between resonance structures. So we'll start by reviewing formal charge. So we looked at formal charge in the do now, but the whole point of formal charge is to help us decide which Lewis structure is the best, which one represents the actual structure of a molecule. And so the best structure, like what we looked at in the do now, the best structure is the one that has the most atoms with a 0 formal charge. And if there has to be a formal charge, it puts the negative on the more electronegative atom. And so what I want to do is I want to look back at CO2. So in the do now, we looked at carbon dioxide. And I had said that we could technically have 2 different structures of CO2. Now, if we calculate formal charge for each atom in carbon dioxide, oxygen has 6, carbon has 4, oxygen has 6 in terms of valence electrons. But there's 2, 4, 6 electrons in the circle, formal charge is 0. 1, 2, 3, 4 electrons in the circle, formal charge is 0. 1, 2, 3, 4, 5, 6 electrons in the circle, formal charge is 0. So for carbon dioxide, when there are 2 double bonds, the formal charge on every atom is 0. That's the best structure that we could have if all the formal charges are 0. Now, I'm just going to look at the other one with the triple bond just to show you why we don't ever see this structure. We only ever see this structure up here with carbon dioxide. And that's because 2, 4, 6, 7 electrons, that's -1. Carbon has a formal charge of 0. This oxygen has a formal charge of +1. So notice when we compare the two, this bottom structure, 2 of the atoms have a formal charge. This one up here, they're all 0. So we don't ever see carbon dioxide with a triple bond and a single bond. We only ever see it with 2 double bonds. Which is why a lot of times we will say that the more symmetric the molecule, the more dominant that structure is, which is true, but our reasoning is because the formal charge is 0 for every atom. And that's it with formal charge. So the big questions with formal charge is, can you calculate formal charge? And then based on formal charge, could you tell which one is the best? And that's the one with the most atoms with a formal charge of 0. And then, really quick, we'll look at resonance. So resonance, this exact picture is at the bottom of the video 10 notes, so page 11 of your notes packet. This is right at the bottom. So resonance structures, we didn't even look at yesterday. I didn't have you draw Lewis structures that more than one structure could be drawn, because we're going to do that today. But in a resonance structure, for example, if you needed to draw carbonate, CO3 2-, when you draw carbonate, you put carbon in the middle and 3 oxygens around, and you notice this has the potential to multiple bond. So you do the 6n+2 rule, and you see that you need 1 double bond, because there's a difference of 2. But when you draw CO3, one person could draw the double bond here, one person could draw the double bond here, another could draw it up here. And they're all correct. If you can draw the double bond in more than one place, that means that we have resonance structures. You have to show every possible structure if resonance exists. Now you have one of 2 ways of showing it. You could show it like this with the double-headed arrows, or you could use the dotted line. The dotted line shows where the possible location of the double bond could be. Whichever way you pick is up to you, but you have to make sure that you are consistent. I'll show you an example of the dotted line on the next page as well. With resonance structures, because the double bond can move, that means that all three of these bonds are actually the same length. They're an average. So we have, when we look at bond order, right, bond order is the number of bonds between 2 atoms. We could have a double bond here, we could have a double bond here, we could have a double bond here. So we have 4 bonds that exist between 3 atoms. So the bond order for each CO bond is actually 4/3, 4/3, because we have 4 bonds between 3 atoms. So it's an average. The length is the same for each. Because it's an average of all of them, these bond lengths are going to be somewhere between a single bond and a double bond. So it's not just a single bond, it's not just a double bond, it's somewhere in between, because that double bond can move and it's a resonance structure. So you just have to make sure, if you have resonance, that you are showing all of the possible structures. So a couple extra examples, if you have CO2H, that's a resonance structure. You could draw the double bond between the top oxygen or the side oxygen. Notice you can't put the double bond between C and H, because H can't multiple bond. But you still have to show all of the possible structures. And then another example of the nitrate ion, NO3-. This shows that dotted line way of drawing resonance. So the dotted line is a bond that's found in at least one of the resonance structures. So it's that double bond that's moving around. If you draw this dotted line representation, you have to show a solid line for the bond that is in all structures. And then in terms of lone pairs, you only show the lone pairs in these dotted line structures. You only show the lone pairs that are found in all of the resonance structures. So that's why it actually looks a little bit different than if you drew NO3- for each resonance structure. So what I'm going to have you guys do is I'm going to actually have you guys work through the practice with a partner, with a group. There is one addition that I want you to add. So if you're in your notes packet and you flip to page 12, so it's the very last part of chapter 8. The rest of it is just extra Lewis structures notes. But at the bottom of page 12, for number 7, the actual question got cut off somehow. So for number 7, make sure that you just write the actual question. What is the bond order of each bond? So for number 7, make sure you add the question, what is the bond order for each bond? Otherwise, if you just read number 7, it's just a statement. And so it's only the one page for the practice. 1 through 5 is having you practice draw the resonance structures. You want to draw them on the desks instead of on the paper, that's okay. And then 6 and 7 are practice AP style questions. And then 8 is similar to what we looked at in the Do Now with Formal Charge.